Welcome all. Today we are going to discuss about the Newton-Raphson method. The Newton-Raphson method is used to find the root of the equation. The Newton-Raphson method is also known as the Newton's method, which is used to find the root of the function f of x. Suppose we have the function f of x, then to find the root of the equation, we use the Newton-Raphson method. The Newton-Raphson method is very simple and fast. The number of iterations required are less as compared to the bracketing method in case of Newton-Raphson method. The computation is very fast and simple. The one drawback of this method is it uses the derivative f dash of x of the function as well as the f of x itself. The only problem with the Newton-Raphson method is what it requires the continuous and differentiable function. Hence, the Newton-Raphson method is usable only in the problems where f dash of x can be easily computed. If the function f of x is in such a way that the computation of derivative of f of x is difficult, in that case it is not suitable to use the Newton-Raphson method. The Newton-Raphson method is also known as the Newton's method. Here again we have to assume f of x which is continuous and differentiable, and the equation is known to have a solution near to the given point. Here we have to assume the initial guess in such a way that it should lies near to the given point, that is near to the solution. That means we have to check the convergence of the condition so that we can get the answer easily. Suppose the graph is shown which is having the equation y is equal to f of x. Then suppose this is the solution which we have to find, this is the root of the equation which we have to find. Then the first initial guess we will assume as a x1. Suppose x1 is the first initial guess. Then project the x1 on the curve to get the f of x. Then draw the tangent from the point f of x1. Then we will get the next point as a x2. Then x2 is the next iteration solution. After projecting the point on the curve, we will get f of x2. From the f of x2, again if you plot the tangent, then you will get the point x3. After x3 you will get x4, and after x4 you will get the solution. Likewise, you have to progress the solution towards the exact point which is the root. In this case, the convergence is the main criteria, so that the nature of the curve is very important. The nature of the curve decides whether we will get the solution by Newton-Raphson method or not. The solution process starts by the selecting of point x1, that is the initial guess x1, as the first estimate of the solution. That is first estimate of the solution. The second estimate x2 is found by drawing the tangent line to the f of x at the point is x1 comma f of x1, and determine the intersection of the point of tangent line with respect to the x-axis. As shown in figure, we can get the point x2 which is the next iteration solution. Now check the convergence criteria. The next estimate x3 is the intersection of the tangent line f of x at a point x2 comma f of x2 with the x-axis and so on. The slope f dash of x1 of the tangent at a point x1 comma f of x1 can be written as f dash of x1 is equal to f of x1 minus 0 upon x1 minus x2. Let us see once again. F dash of x1 is equal to f of x1 minus 0 upon x1 minus x2. If you rearrange this equation, you will get x2 is equal to x1 minus f of x1 upon f dash of x1. Let us see once again. x2 is equal to x1 minus f of x1 upon f dash of x1. This is the formula for the Newton-Raphson method. Suppose instead of 2 here is a 4, then instead of x1 here will be a 3. The equation can be generalized for determining the next solution. The next solution is xi plus 1 from the current solution. The current solution is xi. xi is the current solution and xi plus 1 is the next solution. So the next solution is given by xi plus 1 is equal to xi minus f of xi upon f dash of xi, where f dash of xi is the first derivative of the function f of x. xi plus 1 is equal to xi minus f dash of x. Xi plus 1 is equal to xi minus f of xi upon f dash of xi. The algorithm for the Newton-Raphson method is: first, select a point x1 as an initial guess for the solution. Then for the I is equal to 1, 2 until the error is smaller than the specific value, compute the xi plus 1 using the Newton-Raphson equation. The Newton-Raphson iteration formula is given by I is the iteration number. So xi plus 1 is equal to xn minus f of xi upon f dash of xi. Consider this whole value as a phi of xn. Consider this whole value as a phi of xn. Hence x is equal to phi of x. Hence x is equal to phi of x. The convergence condition is if mod value of phi dash of x should be less than 1. Convergence condition is mod value of phi dash of x should be less than 1. If the phi dash x value is greater than 1, that means it is the divergence condition. For that case, we have to assume the next initial guess again. Here we have just replaced the values, hence we can get phi of x is equal to x minus f of xi upon f dash of xi. Phi of x is equal to x minus f of xi upon f dash of xi. Now to check the convergence condition, take the first derivative of phi of x. To check the convergence condition, take the first derivative of phi of x. So the first derivative is 1 minus in bracket f dash of x bracket square minus f of x into f double dash of x upon f dash of x bracket square, where f dash of x is the first derivative, f double dash of x is the second derivative. Just rearrange this equation, you will get phi dash of x is equal to f of x into f double dash of x upon f dash of x bracket square. F dash of x is the first derivative, f double dash of x is the second derivative. Hence, the mod value of phi dash of x is equal to mod of f of x into f double dash of x upon f dash of x bracket square. This is the convergence condition. So the convergence condition is the Newton-Raphson method converges if the mod value of f of x into f double dash of x upon f dash of x bracket square is less than 1. If it is greater than 1, that is the divergence condition. Hence, the rearranging the equation, we can get mod value of f of x into f double dash of x is less than f dash of x bracket square. After rearranging, we can get f of x into f double dash of x is less than f dash of x bracket square. So this is the convergence condition for the Newton-Raphson method. Now let us take the example. So the example is, find the root of the equation x raised to 4 minus 11x plus 8 is equal to 0 accurate up to the 5 decimal places. Equation is given in the form of x raised to 4 minus 11x plus 8 is equal to 0 accurate up to 5 decimal places. So the function is f of x is equal to x raised to 4 minus 11x plus 8. Now check the first derivative of the function. First derivative is f dash of x is equal to 4x cube minus 11. X raised to 4 derivative is 4x cube, 11x derivative is 11. As 8 is the constant, the derivative of constant is 0. Hence, we have f dash of x as 4x cube minus 11. Let us take the first initial case as a x0 as a 2. Then f of x0 means replace the value of x by the 2. So f of x0 is f of 2 is equal to 2 raised to 4 minus 11 into 2 plus 8, which gives us the answer of f of x0, that is f of 2 is equal to 2. Next is f dash of x0. Replace the value of x0 by the 2. So f dash of 2 is equal to 4 2 cube into 4 2 cube minus 11, which gives us the answer 21. Hence, we have the two values as x0 is 2, f of x0 is 2, f dash of x0 is 21. Now the next thing is we have to find the next iteration as x1. Hence x1 is equal to x0 minus f of x0 upon f dash of x0. We have calculated the value of f of x0 and f dash of x0 previously as a 2 and 21. Just replace that values, you will get x1 as a 1.90476. x1 is 1.90476. x2 is the next iteration value. The next iteration value is given as x2 is equal to x1 minus f of x1 upon f dash of x1. x2 value is given as x1 minus f of x1 upon f dash of x1. Just replace the value of x1 1.90476 in this equation. We will get 1.90476 minus 1.90476 raised to 4 minus 11 into 1.90476 plus 8 upon 4 into 1.90476 cube minus 11. If you compute this value, you will get x2 as a 1.89209. x2 as a 1.89209. Now for the next iteration, x3 is equal to x2 minus f of x2 upon f dash of x2. So the replace value of x2 as 1.89209 minus 1.89209 raised to 4 minus 11 into 1.89209 plus 8 upon 4 into 1.89209 cube minus 11. If you compute this value, you will get the answer as 1.89188. x3 is equal to 1.89188. x4 is equal to x3 minus f of x3 upon f dash of x3. If you replace the value of x3 as 1.89188 minus 1.89188 raised to 4 minus 11 into 1.89188 plus 8 upon 4 into 1.89188 cube minus 11, which gives us the answer as 1.89188, which is similar to the x3. As x3 and x4 are same, so we can say this is the converged answer, or this is the exact answer we can get from the Newton-Raphson method. That's why the root of the equation is 1.89188. Now let us solve the next example. So the next example is evaluate the square root of 29. Evaluate the square root of 29 up to the 5 decimal places by the Newton-Raphson iterative method. Hence our equation is x is equal to root of 29. Taking the square on both sides and rearranging the equation, we can get x square minus 29 is equal to 0. x square minus 29 is equal to 0. So f of x is x square minus 29 is equal to 0. F dash of x first derivative is 2x. X square derivative 2x, 29 derivative 0. Now let us check xi plus 1 is equal to xi minus f of xi upon f dash of xi. This is the Newton-Raphson formula. We just replace the values of these in this equation. We will get xi minus xi square minus 29 upon 2xi. Just rearrange this equation. You will get 1 upon 2 in bracket xi plus 29 minus xi. Sorry, 29 upon xi. Now we will check the first iteration or initial guesses. So just take the value of f of phi. Phi I have selected randomly to check the initial guess. So f of phi is x square minus 29. So replace x by phi. So x square minus 29, that means phi square minus 29, that means 25 minus 29 is equal to minus 4, which is less than 0. So this is the convergence condition. Let us check another. F of 6 is equal to 36 minus 29, which is 7, which is greater than 0. So obviously our answer f of x0 lies in between 5 and 6. So take the greater than value for the initial guess as a 5.3. So x0 is 5.3 in my case. So suppose xi is equal to 1 by 2 into 5.3 plus 29 upon 5.3, which gives us the answer 5.38585. For the x2, replace x1. So x2 is 1 by 2 5.38585 plus 29 upon 5.38585, which gives me the answer as 5.38516. For x3, replace the value of x2. I will get 1 by 2 5.38516 plus 29 upon 5.38516, which gives me the answer as same as that of x2. So x2 and x3 is same. So we can say this is the answer. As x2 as x3 are same up to 5 decimal places, we can say root of 29 is equal to 5.38516. Root of 29 is 5.38516. So this is the answer by Newton-Raphson iterative method. Thank you. Welcome all. Today we are going to discuss about the flowchart of the bisection method with the help of accuracy criteria. There are two types of bisection methods. First is accuracy criteria and second is iteration criteria. Today we will learn about the accuracy criteria. Firstly, we have to define the function. That function is y. Then we have to find the y is equal to f of x. It is the given function. Then we have to give the inputs as a x1 and x2 as a initial guesses and accuracy as a input. Then x1, x2 and accuracy, these are the three inputs which are required for solving the bisection method problem with the help of accuracy criteria. Then we will find the y1 as a function of x1, y2 as a function of x2. y1 is equal to f of x1, y2 is equal to f of x2. Then we will check the convergence criteria. The convergence criteria is y1 into y2 should be less than 0. If y1 into y2 is greater than 0, then we have to give the value of initial cases. Again, we have to give the new value of x1 and x2. Hence, here we have taken the condition as while y1 into y2 is greater than 0, then read the value of x1 and x2 again. Then again calculate y1 and y2 and again cross check whether y1 into y2 is less than 0 or greater than 0. This loop continues until the value of y1 and y2 is less than 0. Then we will check the answer by bisection method. That bisection method answer is x3 is equal to x1 plus x2 by 2. We check the respective value of y1, y3. That value is f of x3. We have to check this value for the accuracy criteria. That's why we have taken the modulus value of x1 minus x2 or x2 minus x1. This is the mod value. It should be less than accuracy, then and then that will be our answer. But in case of x2 minus x1 is greater than accuracy, then we will check the following condition. That condition is if y1 into y3 is less than 0, then if this condition is true, then we will replace x2 by x3. Similarly, y2 will be getting replaced by the y3. If y1 into y3 is less than 0, this condition is not true, then we will replace x1 by x3. Similarly, y1 is replaced by y3. We have to continue this loop until the x2 minus x1 value should be less than accuracy. If the value is coming greater than accuracy, then this loop will continuously execute. If this loop, when you want to stop the loop, at that condition the x2 minus x1 should be less than accuracy. Once the x2 minus x1, the mod value of x2 minus x1 is less than accuracy, then at the next step, that will be our answer, x3 is equal to x1 plus x2 by 2. Then finally we print the answer x3, and this is the end of the flowchart. So in this case, the flowchart is divided into 3 portions. First is the input values, then checking convergence, and third one is the checking the value of y1 into y3 to replace the x2 or x1. Here we decide which value we have to replace by this equation. So this is the procedure to solve the problem by the bisection method with the help of accuracy criteria. Thank you. Welcome all. Today we are going to discuss about the successive approximation method by the accuracy criteria. Today we will discuss about the flowchart of the same. Firstly, our flowchart starts from start to define the function, that is g of x. Then we define the function dg of x. dg of x is the first derivative of the g of x function, and g of x is the any function which we convert in the form of x. Then as an input we consider x1 as an initial guess and accuracy. As we are dealing with the accuracy criteria, the inputs are initial guess x1 and accuracy. Then we will check the convergence condition. The convergence condition is A, which is given as a dg of x1. Means we have to check the value of function in the first derivative of g of x, in which we replace x by the x1. Then if convergence is greater than 1, then we will follow the next initial guess. We have to search for another initial guess because this is the divergence condition and we need the convergence condition. While a is greater than 1, this is the divergence condition. That's why we will read the value of x1 again. Then once the value of a is less than 1, this loop will not execute. Then we find the value of x2 as a g of x1, and again we find the value of accuracy until the value of convergence is less than 1. Once the value of convergence is achieved, then we will check for the accuracy criteria. For the accuracy criteria, we check modulus value of x1 minus x2, which should be less than accuracy. If the value of x1 minus x2 is greater than accuracy, then we will replace x1 by x2 and the next value of x2 will be g of x1. We repeat this loop until the value of x1 minus x2 is less than accuracy. Once the value of x1 minus x2 is achieved less than accuracy, this loop stops to execute. Then our final answer will be x2 is equal to g of x1, and we then print the root as a x2. So successive approximation method divides into three portions. First is the input values, then second is the checking the convergence criteria, and third checking the accuracy. So this is the successive approximation method by the accuracy criteria. Thank you.